I'm pleased to introduce our second speaker, Professor Nancy Hingston from the College of New Jersey. She received her PhD from Harvard University in 1981, and her thesis advisor was Professor IL5.5. And she was a member of the Institute for Advanced Study 5 times. And since 1990, she has been at the College of New Jersey. And today, she will talk about loop products, Poincare duality, index growth, and dynamics. Let's welcome her.
Thank you. I'm honored by the invitation. It's wonderful to be here, and thank you for coming to my talk. So, here's a list of some of the main ideas that will appear in this talk. From topology, you have loop spaces, loop products, and what I call Poincare duality in loop spaces. The original motivation for this work came from geometry, from closed geodesics, and from iteration and index growth. And at the end, I'll give some applications of the topology to problems in geometry, to resonance for loop homology of spheres, and I'll briefly mention some analogs in floor theory. And Morse theory, of course, is the bridge that connects the topology with the geometry. So we'll start off with M, a compact-oriented manifold with a Riemannian or Finsler metric. I'm going to assume that M is simply connected just for simplicity. And I will also assume that all homology and cohomology is taken with rational coefficients, although that is also just for sake of simplicity. There are more general statements are possible. So let's see how this works here. See that? Lambda M is the free loop space. This is the space of all maps from the circle to the manifold M. So it's the space of loops on M. And inside the free loops we have, this is the base loops, the topologist loop space. This is the space of maps from the circle to the manifold that take the base point to the base point. And these two spaces naturally have the structure of infinite dimensional spaces, but they also have finite dimensional approximations, beautiful finite dimensional approximations that are due to Morse, and that I think could be used more nowadays than they are. The natural functions on these two spaces are the length function and the energy function. The function I'm going to use for technical reasons, I'll be using this function f, which is the square root of the energy function. It's also the L2 norm of the derivative. So let's see. It's the square root of the integral of the velocity squared. And this function has the property that it's greater than or equal to the length function with equality if and only if the loop has constant speed, or if and only if it's parameterized proportional to arc length. And you won't go wrong in this talk by just thinking of f as the length function. I might call it the length function from time to time too. It's more or less the length function. And we're interested in this function because the critical points of f are the closed geodesics on M in the given metric. Which brings us to this old problem, to find closed geodesics on a given Riemannian manifold M. So this problem goes back to Poincare, Birkhoff, Morse, Bott, Einweiser, many other authors. I have pictured here a Riemannian manifold, and as has been mentioned at this conference already, but I'll say it again. On a Riemannian manifold, we have a distance function, and a geodesic is a curve that locally minimizes the distance between 2 points. And if you start at a point on the manifold, and if you have a direction, then there's a unique geodesic starting at this point in that given direction. And if the manifold is compact, the geodesic can be continued in both directions forever and ever. And I'm waiting now. I've drawn this geodesic, and I'm waiting to see if at some point it will close up and become periodic. What do you think? Maybe. So going back to Morse, Morse theory gives us a link between the topology of the free loops and the critical points of F, which are the closed geodesics. So here's one way to describe the way this correspondence works. If you have a homology class H, little h, on the free loops, you can get from that a real number, which is the critical level of H. The critical level of H we define to be the infimum of all real numbers A, so that H can be represented in the loops of length less than or equal to A. So it's the critical level or the minimax level of H. And here's how I think of it. We have this big space, lambda, the free loop space, and as Miller taught us all, we take the function to be the vertical axis, and if we take the vertical axis to be the f-axis, then the function is the height function. And we have if we take a representative for a homology class on the space, we push it down as far as it can go, and when it gets stuck, we found the critical level of the homology class. And it is a fact that the critical level of H is a critical value of F. And therefore there's a closed geodesic gamma whose length is this critical level and whose index is approximately the degree of the homology class, the dimension of the homology class. Now, this index here is the Morse index. So if gamma is a critical point, then that means that all the partial derivatives of F vanish at gamma, and the index is the dimension of a maximal subspace of the tangent space in which the second derivative is negative definite. And in this problem, that's always finite. So if we have a homology class, we can get out of it a critical level, a closed geodesic. Can we then try to count closed geodesics by counting homology classes? Now, this lambda is a big space, it's an infinite dimensional manifold, there's lots of independent homology classes, so you might think lots of homology classes, lots of closed geodesics, but there's a problem with that. And this problem is the problem of iteration. So if gamma is a closed geodesic, so also are all of its iterates, gamma squared, gamma cubed, gamma to the fourth. So these have the same image on the manifold, but they go around more times. So they're different points in the free loop space, but geometrically you don't want to count them as being different. And they have different critical levels. So if gamma has length L, this has length 2L, this has length 3L, so they have different lengths. And they have, in general, they have different indices. So here is a sort of a schematic picture of the free loop space. So again, I'm picking the f-axis to be the vertical axis, and we have this big manifold, and what this is illustrating is the fact that one geometric closed geodesic actually appears in the free loop space as an infinite collection of critical points with different critical values. So there's no hope, it seems, of counting the closed geodesics by counting the critical values or by counting homology classes. However, there is a famous theorem due to Grommel and Meyer, which tells you that if you have lots and lots of homology classes, then you can get lots of closed geodesics. And here's how this works. I think you should be able to understand the outline of the proof here. So Bott proved in 1956 that the index of each closed geodesic grows approximately linearly. And Grommel and Meyer proved in 1969 that the rank of the homology of the iterates of any fixed closed geodesic is bounded. So what that means is that if you pick one closed geodesic and you look at all of its iterates, the index in which the homology appears grows approximately linearly. Meanwhile, the amount of homology that comes from any given iterate is bounded, and therefore the contribution in any given dimension is bounded from any any particular closed geodesic and its iterates. And therefore, if the rank of the homology of the free loop space is unbounded, you can conclude that M has infinitely many closed geodesics for any metric whatsoever. So that's the theorem of Groman and Meyer. And Sullivan and Viguet-Poirier settled in 1976 the question of when this criterion is satisfied. They showed that the rank of the homology of the free loop space with rational coefficients is unbounded if and only if the cohomology ring of M with rational coefficients and the cup product requires more than one generator. In other words, if it's not just a truncated polynomial ring with one generator, which is what this is supposed to represent. So according to this, most manifolds will have infinitely many closed geodesics for any metric. However, some of the simplest and nicest and our favorite manifolds, the theorem does not apply to. So spheres and projective spaces, the cohomology ring only needs one generator, and therefore the rank of the homology of the free loops is bounded. And typically there's the rank in any given dimension is 0, 1, or 2. Although there's non-trivial homology in infinitely many dimensions, it's bounded. And therefore the theorem does not apply. And it is not known if there's a metric on a sphere or a projective space. I should have said a Riemannian metric here. This should say Riemannian metric typo. It's not known if there's a Riemannian metric on a sphere or projective space with only finitely many closed geodesics. However, there are some very interesting partial results. There are infinitely many closed geodesics for any Riemannian metric on a two-sphere. This very nice theorem took almost a century to prove. There are infinitely many closed geodesics for a generic metric on any sphere. By the way, when I say sphere, I mean n is bigger than 1. I don't think the S1 is a sphere. There are, however, examples. These are beautiful, beautiful examples due to Katak of non-symmetric Finsler metrics with only finitely many closed geodesics. Now, for our purposes, the difference between a Riemannian metric and a Finsler metric is that the Finsler metric is not required to be symmetric. So if you take the length of a vector and you take the length of minus the vector, they might be different. And you might not think that makes a lot of difference, but in this case it does. However, it is known that there are at least 2 closed geodesics on each non-symmetric Finsler S2, and therefore there are at least 2 closed geodesics on every Finsler S2 whatsoever. This was proved by Yiming Long and by Victor Banger, and 2 might not seem like such a big number, but this is sharp. This is sharp due to these examples. So I have been thinking about trying to find closed geodesics on spheres and projective spaces for a long time, and at some point you seem to be sort of inevitably led to the following question. Is there an algebraic operation on the homology of the free loops that corresponds to iteration of closed geodesics? And the answer is sometimes. And this brings us to the topic of products on loop spaces. So this is the candidate here. Okay, so I'm going to begin with the Poincare product. This is the oldest product. This is a product on the homology of the base loops. Okay, so it's a loop product, in other words. So I'm going to assume that we're given 2 cycles, x and y, and I'm going to pretend that a cycle is just a subset of the base loop space. And so given these 2 cycles, then the Poincare product of x with y is defined to be, or is not defined to be, is represented by the space of all loops of the form alpha star beta, where alpha is an x and beta is an y, and alpha star beta means first you go around alpha and then you go around beta. Right, so this space is parameterized by the Cartesian product of x with y, and that's why it gives you a map from the j-dimensional homology of, if you put in a j-dimensional cycle and a k-dimensional cycle, you get something out of dimension j plus k. That's the Poincare product. And here's some examples. Example of the sphere. Here's some cycles on the base loop space. So first of all, by a circle on a round sphere, I mean the following thing. A circle on the round sphere is the intersection of the round sphere with some plane, not necessarily through the origin. If the plane goes through the origin, then it's a great circle, and if the plane doesn't go through the origin, it's a not so great circle, but it's still a circle. And so I'm going to take, this is a picture of my sphere here, and the base point is there at the bottom of the sphere, and I'm going to pick a vector at the tangent space at the base point, and I'm going to define for you a cycle. This is the set of all circles beginning at the base point with this given tangent direction v. And it has degree n-1. This is a very basic cycle from topology. Anybody who's worked with loop spaces will recognize, we see this. It's the most basic cycle. Here's another cycle. It's a pretty boring one. U is just the constant loop at the base point, which is pictured down here. This one has degree 0, this one has degree n-1. So let's compute some Poincare products. What is the Poincare product of U with A? Well, the Poincare product of U with A is represented by loops of the form, first you take this guy, and then you take one of those. And I hope it's obvious that that is just homologous to the class A, right? And in fact, this U is the identity element in the Poincare ring. And so the next question is, what is A star A? So a typical loop in A star A consists of two of these loops glued together. Now, what is A star A? Well, it turns out it's not 0. In fact, if you take the m-fold Poincare product of A with itself, it's never equal to 0. And we say that A is non-nilpotent in the Poincare ring. And in fact, the homology of the base loops is a polynomial ring in this generator A. This Q is just a coefficient. If we had different coefficients, this Q would be different. Okay, so now what about the critical levels here? Well, the critical levels depend on the metric. This information does not depend on the metric, but the critical levels depend on the metric. Well, I guess for any metric, the critical level of U is 0, right? It just consists of one loop with length 0. The critical level of A is 2 pi. I hope it's at least intuitively obvious that this collection of circles cannot be continuously deformed below the level 2 pi. So the critical level of A is 2 pi. Now, what about the critical level of A star A? Well, it's at most 4 pi, right? It couldn't be bigger than 4 pi. And it must also be a multiple of 2 pi because the critical level has to be a critical value of the length function, right? And in the round metric, all the geodesics have length a multiple of 2 pi. So here's an exercise. And we also know that A star is not trivial, but here's an exercise. It's actually not that easy, but you can show that A star A is actually homologous to the space B of all circles beginning at the base point, with all possible tangent vectors. This has degree 2 times n-1, but this is at level 2 pi. So in fact, the critical level of A star A is 2 pi, not 4 pi. And the critical level of A to the 2m-1 is the critical level of A to the 2m. They're both equal to m times 2 pi. So we say that, remember A is non-nilpotent in the group, but we say that A is level nilpotent to mean that the level drops. So the critical level of A to the m is less than m times the critical level of A for some m. Okay, so next comes the Chas-Sullivan product. This is a product on the homology of the free loops. This appeared in a preprint in 1999. It was never published for reasons which I'll say a little bit about later. So we're given cycles x and y. Again, these are now on the free loops. The base point's not tied down. And again, I'm going to pretend that cycles are just subsets of the manifold, although I'm going to assume in a minute that they're actually submanifolds. So I'm going to assume that the base points of x and the base points of y are transverse. So E here is the evaluation map that evaluates a loop at the base point. 0 here is the base point of the circle. That's what the role of 0 is playing here. And so again, this means that the base points of x and the base points of y are transverse. And under that condition, here's the definition of the Chaz-Sullivan product. It's represented by the space of all loops of the form A alpha star beta, where alpha is in x, beta is in y, and alpha of 0 is beta of 0. So they have the same base point. So this gives us, it's, you know, there's something to be proved, of course, but it gives us a well-defined map from the j-dimensional homology tends to the k-dimensional homology to the j plus k minus n-dimensional homology. We lose n here because of this. This is a codimension n condition that alpha of 0 equals beta of 0. So this is the Chaz-Sullivan product. So here's some examples on the sphere. So here's some new cycles on the free loops that we didn't have in the base loops. Here's the cycle C. C consists of all great and small circles. This has degree 3 n minus 2. You can work that out. Here's a picture of C. E has degree n. This is the space of all constant loops on the sphere. And then we have these other guys from before. These came from the base loops, but now we have them on the free loops. And here's just a couple of computations. If you take the Chaz-Sullivan product of C with E, that consists of all the loops. It's represented by all the loops of the form one of these, followed by one of these, but only if the base points are equal. And I hope it's clear that that's just C again, right? That's homologous to C. What's the Chaz-Sullivan product of A with itself? Well, I should have made you guess, but I don't know how to make the lines clear one at a time. The Chaz-Sullivan product of A with itself is equal to 0. In fact, if you take any class from the base loops and any other class from the base loops and take their Chaz-Sullivan product, it's equal to 0 because the base points of this just consist of a point, and the base points of this just consist of a point, and you can make two points transverse by making them disjoint, and then it's parameterized by the empty set. So one more computation, the product of C with U, the Chaz-Sullivan product, consists of all loops of the form one of these, followed by this guy, but they have to have the same base point. And what's that? I should make you guess for this too. That's B, right? That's the space B. So it is a fact that this class C, the class of all circles great and small, this is a basic homology class on the free loops. It's very important, and its powers are all non-zero, and it's also level nilpotent with the standard metric. Now, it is a fact that the homology ring of the free loops with the Chaz-Sullivan product is finitely generated. What I've showed you on previous pages, almost a complete set of generators. And this ring was computed for spheres and projector spaces by Cohen, Jones, and Yan in 2008. They didn't use this geometric method, they used the spectral sequence. There's a typo here. For the fibration, it should just be from it's the fibration of the free loops over the manifold M, and the fiber this is the fiber, not the base. And the Pontryagin product on the homology of the base loops. So yes, so the Pontryagin ring and the Chaz-Sullivan ring are very intimately linked using this spectral sequence and this vibration. Now, I should also add that this beautiful definition of Chaz and Sullivan turns out to be more or less completely unworkable because of this transversality condition. And alternate definitions of the Chaz-Sullivan product have been given. The first one was by Cohen and Jones, I think, in 2002. So there are more rigorous definitions than what I gave you, but it's still the best way to think about it. Okay, so the cycles A, B, C, E that I just showed you on the free loop space, and their Chaz-Sullivan products. In particular, when you multiply any element with that class C, consisting of all circles great and small, that's always objective on the homology of the free loops. And all of these cycles and their Chaz-Sullivan products would have been very familiar to Morse. This exact same geometry appears in his calculus of variations in the large, where he's interested in the topology of loop spaces because he's trying to find closed geodesics. And the same geometry appears in the work of Bob Samuelson on manifolds, all of whose geodesics are closed. So it's interesting in a way that the spheres and the projector spaces are spaces that have metrics where all the geodesics are closed. And they're also the spaces where it's hard to prove for a general metric that there are any closed geodesics whatsoever. Anyway, so I first encountered the Chaz-Sullivan product. I was sitting at lunch at the Institute for Advanced Study, and I heard somebody give the definition of the Chaz-Sullivan product. I got very excited. I jumped up and I said, I know that product. I said, Morse knew that product. And then I said, where's the other product? The reason I said, where's the other product, was the following. There's this persistent symmetry. Persistent symmetry in the geometry of loop spaces and closed geodesics. And it corresponds roughly to turning the loop space upside down. And so just flipping the whole thing. Now, I have to try to explain to you why I think of that as being Poincare duality. I don't know if that's a good name or not, but here's why I think of it that way. Let me review for you what Poincare duality looks like on a finite dimensional manifold in the presence of Morse theory. So suppose now that I have a compact orientable manifold of dimension n, and let's say Morse function to keep things simple. Then Poincare duality asserts that there's an isomorphism between the k-dimensional homology of M and the n minus k-dimensional cohomology of M. So here's what that has to do with Morse theory. The homology of M is computed by the complex of Morse chains. And how do I think of a Morse chain? A Morse chain is an unstable manifold of a critical point of index k. So here's our unstable manifolds labeled U. So these are these downward facing relative cycles. And those are the Morse chains. Now, the cohomology of M is computed by the complex of Morse cochains. Now, what's a Morse cochain? Well, you can think of a Morse cochain as being an upward facing stable manifold. And the reason why that makes sense is because the stable manifold acts on the unstable manifold, or evaluates it by intersection. So according to this analysis, what does Poincare duality do? Poincare duality is reversing F with minus F, just turning the picture upside down. Index becomes co-index. Homology becomes cohomology in the complementary dimension. So that's why Poincare duality means turning things upside down. So now in infinite dimensional manifold, lambda, Poincare duality does not take the form of an isomorphism between homology and cohomology in complementary dimensions. There's no such thing as complementary dimensions. However, it is true that many things work the same when you turn the free loop space upside down. Now, this turns out to be a very powerful principle, although it's not even well formulated. I have seen it work in many examples. I have never yet seen it to fail. So I'm going to show you some evidence, and then you can see for yourself what you think. And also, I would appreciate it if you report to me if you see any further examples of this principle. Okay, so here's the first example. This is the other product that I said, where's the other product? Well, This is joint work with Mark Goreski. Poincare duality predicts the existence of cohomology products. So these are cohomology products on the free loops and cohomology products on the base loops. And these are Poincare dual to Chas-Sullivan product and Pontryagin product. So there should be products of this type. It's absolutely clear what the degree should be. I know this looks weird, but I'll try to explain that maybe in a minute. But Mark and I did show that these products exist, and they're non-trivial. For example, the rings are finitely generated for spheres and projective spaces. Also, these products bear the same relationship to one another as do the Chas-Sullivan product and the Pontryagin product. There's a list of Giesen formulas for these two products. If you write down those formulas and you just turn the picture upside down, you get a list of Giesen formulas for these two products. I'm not telling you what the definition is. It took us a while to come up with a definition. I'm not sure it would help you to see the definition, but the important thing is that they're Poincare dual to these other products. Let me tell you how we actually finally got the definition. We took these two classes, right, and then we pushed them into we restricted these two classes to the finite dimensional approximation. Then we did Poincare duality inside the finite dimensional approximation. Then we did the Chas-Sullivan product. Then we did the Poincare duality again, and then we ditched the finite dimensional approximation. Now, what I said is not quite right, and the reason it's not quite right is the fact that Poincare duality actually works best not in the free loop space, but in the space of free loops that are parameterized proportional to arc lengths. This is just an observed fact. I don't know why it's true. And unfortunately, it's the case that although the finite dimensional approximation is a beautiful, beautiful manifold, its intersection with the space of loops that are parameterized proportional to arc length is not a nice space. So it's more difficult than what I just said. But that's the basic idea, and that's where this product came from. So that's the first piece of evidence. Here's one that has to do with index growth. The Bott formula, remember I told you that the index of the iterates is approximately linear? Well, here's the exact formula from Bott. So if gamma is a closed geodesic, then its iterate, gamma to the n, is also a closed geodesic. And the index of this iterate is bounded below by m times the index of gamma minus some number. And it's bounded above by m times the index plus that same number. So you see the symmetry between the bottom and the top. Now, if there's equality here, then the index of gamma to the m has minimal index growth. And if there's minimal index growth, then there's a non-trivial Chas-Sullivan product. And if there's equality here, then the index growth is maximal. And in that case, there's a non-trivial cohomology product. Here's something about critical levels in Poincare duality. We've defined already the critical level of a homology class as the inf of real numbers such that h can be represented in the loops of length at most a. That's the homology definition. There's a critical level for cohomology. It's the critical level of a cohomology class x is the soup of real numbers a, so that x has support in loops of length greater than or equal to a. So this is the cohomology version. So again, if you have a homology class to find its critical level, you push it down. If you have a cohomology class, you want to find its critical level, you push it up. And these are, from the point of view of geometry, the most important properties of the products. The critical level of the Chas-Sullivan product is less than or equal to the sum of the critical values. And the critical value of the cohomology product is greater than or equal to the sum of the critical values. So it's a different sign here, which is very interesting. And I might also add the cup product does not have this property. The Poincare product and the Chas-Sullivan product both have this property, and both of the cohomology products have that property. So here, as more evidence, here are some old theorems rephrased in terms of products. So I'm going to assume that M is a compact, orientable Riemannian manifold. So Bach didn't prove this. This is a restatement of what Bach proved. Bach proved that if all closed geodesics are non-degenerate, then every homology class is level nilpotent. So eventually the critical level drops. And if all closed geodesics are non-degenerate, same hypothesis, then every cohomology class is also level nilpotent, which means eventually it rises, the level of that rises. Now here are two theorems that I proved, one in 1993, one in 1997. So the first one says if there's a homology class that's not level nilpotent, and the other one says if there's a cohomology class that's not level nilpotent, then M has infinitely many closed geodesics. So these do depend on the metric. These are two different proofs. This one was much, much easier than this one. And it was the guiding light principle of Poincare duality and the fact that this was true that made me sure that the other theorem would be true. Here's just a picture of, let me just say, these are two pictures of the proofs of the two theorems, right? On the left you have the picture of the theorem, the homology theorem. On the right-hand side you have the picture of the cohomology theorem. And so mainly what you have to get out of this is just that one is upside down from the other one. Okay, so that's the end of my evidence of Poincare duality. I hope you found it somewhat convincing. Here are some applications to closed geodesics. This one has to do with a critical profile of a Riemannian manifold. So M is going to be compact and simply connected with a metric G. So Gromov proved the following thing. For every homology class on the base loops, we're going to plot the following point in the plane. The first coordinate is the critical level of H, and the second point is the degree or dimension of H. So we plot these points in the plane, and what Gromov proved is that they lie between two lines that go through the origin. Now, here's a theorem that was proved by myself, joint with Hans-Bert Rademacher. What we proved was the following: if the manifold is actually a sphere with any metric whatsoever, then the same points that I described before, the points of this form, critical value of H, critical level of H, common degree of H, they actually lie at finite distance from one line. They don't spread out. So there's this number, this slope that's associated with the metric, and it has, we call it the mean frequency of the metric. It has units of the number of conjugate points per unit length. And the basic idea of the proof is it uses both of the products. The cohomology product holds this slope up, and the homology product holds that slope down. And we have a proof of this theorem. It uses both products, and I've checked it many times. The reason I've checked it so many times is because I still don't know why it's true. I mean, we can prove it, but I don't really have an explanation. And so let me just skip this, but you can think of Morse theory as coming from the spectral sequence of the filtration that comes from the length function. And what's happening here is that the first page of the spectral sequence looks like this, right? Each closed geodesic has its own little line with its own little slope. And somehow, as the pages turn of the spectral sequence, everything gets lost except things that are a finite distance from a line. They don't have this. Maybe I made the distance too small in this picture. I mean, I'm not asserting about how far those points are from that line. But it is true that if you take any closed geodesic whose average index doesn't put it along the same line, then eventually its iterates have to disappear. Let me just give one more application. Let me just give two more applications. This is one of the consequences for dynamics. So if n is odd, and if we pick a Riemannian metric with quarter-pinched metric, then at least one of the following holds. Either there are two closed geodesics with mean frequency equal to this global mean frequency of the manifold, which is a non-generic condition, or there is a sequence of closed geodesics with mean frequencies approaching this number. So in which case they're definitely infinitely many. So what I think would be an even more beautiful theorem than proving that there are always infinitely many closed geodesics would be to show that either there are infinitely many or there's this very rigid model in which the metric looks, for example, like one of the Katak metrics. Here's some related ideas in floor theory. I just wanted, let me just say a little about this one right here, because I think if I just say the words, you can understand how it's related. I'm making a very long story very short, but many people study the following question. You have a symplectic manifold of dimension 2n, simply connected. We look for periodic orbits of the Hamiltonian flow of a periodic Hamiltonian function. Then myself and Ginsburg and Garel proved the following thing, that there are infinitely many periodic orbits when the pair-Pants product is level nilpotent. So this is exactly the same geometry. This is actually the statement of the Conley conjecture. So it was this statement that proved the Conley conjecture, although it wasn't stated exactly in this form at that time. Recent and current work. Let me just, the last one is this is, I'm especially interested in formulating this principle of Poincare duality. Thank you.
Are there any questions? Okay, let's thank our speaker again. The ICM